Sorry you can't see me today. I'm not feeling very well and not looking too good either, so just recording this from a different device. Hope you're doing okay. This week we'll be looking at volume. Here are the formulas you'll need for this unit. You can use these volume formulas on your work as a formula sheet, so no need to memorize these formulas. In contrast to the last several weeks of work, we're going to move away from the idea of area and into the idea of volume. So by means of an analogy, think of a stuffed pastry, like this blueberry turnover, and think of the surface area as the amount of two-dimensional pastry shell or dough that is wrapping this object. And think of volume, our new subject, as being the amount of space or filling inside of that object. Area fundamentally dealt with squared units. So if this was 1 inch and this is 1 inch, then this would be 1 square inch, or centimeter and centimeter for square centimeters. And when we answer questions like what is the approximate area, or what is the surface area, or what is the exact area of an object, we're thinking about how many of these blue blocks fit on a space of some shape. Maybe it's irregular, maybe it's regular, or how many of these blue blocks would tile the entire surface of some object. For volume, we look at a similar question, except we'll be dealing with the fundamental unit of a unit cube. So imagine you have a cube with one unit for each of the dimensions, so 1 inch deep, 1 inch wide, and 1 inch tall. Then this will be 1 cubic inch, or replace that with centimeters or whatever unit you want. So the fundamental idea here of volume is how many of these unit cubic units, would fit into or inside of some object. And there are formulas that allow us to do this. Those formulas are the formulas you saw a moment ago on the first page here. An important concept for volume is Cavalieri's principle. So I have a question here for you. Which of these two stacks, the one on the left or one on the right, contains more metal? Well, hopefully you realize that they're going to have the same amount, and if you do, that means you understand Cavalieri's principle. It says that if you take a cross-sectional slice of a group of three-dimensional objects, then as long as those slices have the same cross-sectional area, so each one of these B's here have the same area, then the volumes of these objects, provided they have the same height, will also be the same. Allow me to illustrate with an animation here. Here we have two stacks, sort of prism type shapes, and you'll notice that the volumes are the same even through the deformations. The amount of stuff does not change. And this can become very clear when you see it transferred. Whether it's like this or this, the amount of stuff remains the same. So this is Cavalieri's principle. Now, in general, we deal with solids that have this perpendicular height to it, but even if it were oblique or non-perpendicular, we would still have the same volume. So that's a useful idea. Now, many shapes you'll encounter, just like the past one that you just saw in the previous image, are going to be prisms, which mean that you have a pair of congruent bases on top and bottom that have been translated to create a bunch of lateral surfaces, like you see in this hexagonal prism. And in general, the volume of any prism is the area of the base times the height. Because, as this illustrates, you can think of a prism as just being a bunch of stacks, or a stack of a bunch of copies of the base shape. So you find the area of that base shape and multiply it by essentially how many copies you have, which is the height. I'm not sure why this slide's not loading. So if you look at this formula here for cylinder volume, you have pi r squared h. And if you look carefully, you'll recognize this first portion of it. Pi r squared, of course, is just the area of a circle. So pi r squared h is simply a circle area, the area of the base, times the height, or the height of a stack, or the amount of a stack of circles, pi r squared, with a height of h. So a circle prism is simply what a cylinder is. Now pyramids and cones I have grouped together here in part because they kind of look similar, and also their formulas are very similar as well. You'll notice both of these formulas have a 1/3 accompanying them. I want to show you where that 1/3 comes from. So here you see a cube on the right and a pyramid being filled. They have the same base and height, and you see it takes precisely 3 to fill it up. So the pyramid is 1/3 of the cube. So in general, the cube's volume is length times width times height. Let's say it's a prism and not just a cube. Then the pyramid would be 1/3 length, width, and height, as you can see here. And the same is true for a cone as well. So again, a cone's sort of, parent or sibling, depending on your perspective here, its relative is a cylinder. Again, you'll notice here they have the exact same height and same base. That's a requirement here. And you'll notice it'll take exactly 1, 2, and 3 to fill up the cylinder. So the cone is 1/3 of the cylinder. This is the cylinder formula here, times a third. Finally, one of the most interesting applications of volume is the idea of density. Now, in general, I like to think of density as the amount of stuff there is versus the amount of space that it occupies. So in this image here, I think all of us would agree that the second or the right-hand image is the more dense of the two because they have an invariant space. The amount of space is the same. What differs is the amount of stuff inside. So that's what affects the density here. You could also play with the volume and change the volume and therefore change the density as well. Now there is a formula for density. That formula is given on the formula sheet, and it's density equals mass over volume. Sometimes you can use this formula as is. Oftentimes you'll have to modify your use of this formula to apply it in problems. So because there are 3 variables here, you need to know 2 of them in order to find the third. So if you know the density and the mass, you can find the volume. If you know the density and the volume, you can find the mass. And of course, if you know the mass and the volume, you can find the density. So for problems involving density, you either have to plug in, if given, or more likely find one of those values so that you have a total of 2. Again, this will make more sense with some examples this week. And then you have to find the missing third value based on those 2. So find 2 and then plug in and solve for the remaining third. I'm going to leave here on a bit of a teaser. This is the kind of problem we'll be able to solve this week. We're going to start class with this problem. We're identifying a strange rock that's come to your lab. The rock weighs 36.3 grams, or I guess it has a mass of that amount. Weight and mass are not the same, but on Earth they're interchangeable. You then fill a graduated cylinder with a diameter of 5 centimeters with water, and you place the rock in. And as you'd expect, the water level rises 0.5 centimeter due to displacement. So based on this table here, what kind of rock do you think it's going to be? So we'll look at this question next time. All right, take care. Bye-bye.